Hello, everyone. Thank you for having me here. Thank you to the organizers. I am George Perla. I am a PhD student at the National University of Singapore. And this is the last talk of the session. So we've had a full day of great talks about TLA Plus today. But for the next 20 minutes or so, I'd like to share a bit about what's been happening in the world of the lean theorem prover. And specifically, I want to show you Veil, which is a tool we've been building in our group at NUS to tackle some of the same problems that the TLA toolbox tackles, namely testing and verifying transition systems. I am the lead developer of Veil, but it is very much a team effort. It wouldn't have been possible without my colleagues at NUS, Joanne, Vova, and our advisor, Ilya, as well as the interns we've had along the years, Elad Kinsbrunner, who's at Technion, and Ziyu Mao, who's a PhD student at HKU. Vova is also in the room here. You might have heard of Lean before. It's a theorem prover, and it's been getting quite a bit of press recently, especially with all the excitement around AI for math. So this is a headline from the New York Times from, I think, last year. Back in November, Google DeepMind released this system called Alpha Proof, which uses reinforcement learning on lean proofs to do Olympiad-level mathematics, and that created quite a buzz as well. Kevin Buzzard at Imperial College London is working, and he got a big ERC grant to formalize Fermat's last theorem in Lean. But Lean is not only about math. There's also efforts to do software verification in Lean. So Amazon Web Services has this system called CEDA, which is an authorization language that runs in production at AWS. So when you have like roles and policies to check whether certain users can do certain things, that gets checked by CEDA. And CEDA has an implementation in Lean that they've proven correct. And it has a separate implementation in Rust that runs in production, and they differentially test one against the other. And what I find very interesting is that the Lean implementation is faster than the Rust implementation. And when asked why they don't run it in production, then the answer is the engineers don't quite trust it yet. There's also quite a bit of adoption of Lean in the blockchain world. So there's some work verifying, especially cryptographic code with zero-knowledge circuits, and so on. If you're keen to hear more about Lean, Leonardo De Mora, who's the creator of Lean, will be giving a tutorial tomorrow at ETAPS. So I definitely recommend attending that. But I'm not here to talk about the wider Lean ecosystem, of course, but about my own work, which is Veil. Veil is a multi-modal foundational verifier for distributed protocols. Let me break that down and explain what it means. First, Veil is a verifier for distributed protocols. You can, of course, verify arbitrary transition systems, but we focus on distributed protocols. And the point is, if you want to do any kind of reason about distributed protocols, Veil is your tool. Second, Veil is a multi-modal verifier. Multi-modal means you can both test and prove. You can test concretely, similar to TLC, or symbolically, similar to Apalache. You can prove automatically using SMT or other proof automation, or you can prove interactively using lean tactics. Basically, a multi-modal verifier is one in which you can use whatever verification mode best suits you. And you can transition between verification modes seamlessly. Finally, Veil is a foundational verifier. What I mean by this is it makes very few trust assumptions. Veil is entirely embedded in the Lean proof assistant, and the core parts of Veil, of the verifier itself, are formally verified. So for instance, we have a verification condition generator that's proven sound. We have an explicit state model checker like TLC that's proven sound and complete, assuming there are no hash collisions. And you might be wondering, is this actually practical? Can you, do something useful with a formally verified model checker? And I'll get back to that at the end of the talk. But the point is, a major goal of Veil is to keep the trusted computing base as small as possible. Basically, you only have to trust the Veil front end and Lean itself. And that does matter. It might not seem so, but it does matter because there have actually been bugs in these verifiers. So there's this interesting paper from Eurosys 2017 that looked at the correctness of formally verified software, and perhaps surprisingly to some, they found bugs in formally verified software, not in the formally verified parts themselves, but in the shim layer, the networking layer. But in this paper as well, they found 2 or I think 3 bugs in Daphne that for these particular protocols were not crucial, so the protocols were correct, but could have misled a user into thinking their protocol is correct when it wasn't. Okay, so to summarize, Veil is a verifier for distributed protocols embedded in the Lean proof assistant. It has a TLC-style explicit state model checker, which we've proven both sound and complete. It does symbolic model checking by calling external SMT solvers, similar to Apalache. It lets you do proofs using Lean tactics. And because this is all embedded in Lean, it has a small trusted computing base. So I'm going to give a demo. But before I dive into the demo, I'm going to kind of explain the very small protocol I'm going to show you. So this protocol is called leader election in a ring. And it works as follows. So you have a bunch of nodes, and the nodes have unique IDs, and the IDs are totally ordered. So I'm showing them as integers here. And these nodes are distributed in a ring topology. And this is a directed ring. So what I'm showing here is every node can send message only to the node to its right and receive messages from the node to its left. And the way the protocol works is every node sends its own ID to its successor in the ring. So for instance here, node 1 sends its own ID to node 5, node 2 sends its own ID to node 4, and so on. And then the rules of the protocol are quite simple. So when a node receives a message, it looks at the ID in the message, and it compares it to its own ID. So here, node 5 receives this message with ID 1. 1 is less than 5. The rule is you discard the message with lower ID. Similarly, when you receive a message with an ID higher than yours, so here node 1 receives a message with ID 3, you forward the message along the ring. And this kind of continues until you might be able to intuit what happens here. Eventually, all but one of the messages will get dropped. And here, this message with ID 5 gets back to the node with ID 5. And then the rule of the protocol is if you receive a message with your own ID, you declare yourself the leader. So this is a trivial protocol just for demonstration. So here you declare yourself the leader. And the property we're interested in, the safety property we're interested in, is the following, that at any point in the execution of the protocol, there's at most one leader. So I hope people are generally OK with the protocol. So now let me move to the demo. OK, so what I'm showing here is Veil. Veil, as I mentioned, is a verifier embedded in Lean. And what this is, what that means basically is what I'm showing you here is a Lean file. Notice the extension .lean in VS Code with only the Lean extension installed. There's nothing specific with Veil installed. So Veil is a Lean library. You use it in a Lean file by just import Veil at the top. So that's what I'm doing here. And what that does is it makes available to you the entire verifier, its specification language, the model checker, everything. So the way you use it, the way you specify modules in Veil is using this Veil module keyword here. So here we're defining a specification called ring. And now let me go through the specification. So modules in Veil are parameterized state transition systems, similar to TLA, so we have some parameters. Here we have a type parameter, the type of nodes, and this is what we'll instantiate later. Say we want 5 nodes when we model check. But Veil is a bit inspired by Ivy, another tool for protocol verification. So it follows very closely this intuition that it makes sense to model the state of your protocol as a first-order structure. So you can think of this type declaration here as saying, oh, this is an uninterpreted sort in SMT. And we want to both verify and model check this. So we want to make some assumptions about what this sort is. So 2 assumptions we make here is that there's a total order on nodes. And let me go to definition here, command click, and see what that instantiate total order means. So this is a lean type class. I won't go into details what it is very deeply, but the idea is this lets you bundle a bunch of assumptions together into a structure. And what this says is, well, we have a less than or equal to relation, and this encodes a total order with the standard axiomatization of total orders. We also have a similar type class that encodes the ring topology. I won't go into details. You can ask me about this later if you're curious. Now, those are the parameters of the system. Basically, this type node is a parameter. And we're defining a state transition system, so we want to define what is the state of the system, the type of the state. As I mentioned, we take some inspiration from Ivy, and we encourage users to specify their state as a first-order structure, meaning constants, relations, function symbols. But does not require. You can use arbitrary lean types in Veil. So what we're doing here is we have this relation, leader, that encodes effectively the set of nodes who have declared themselves the leader. And then we have a separate relation pending, which encodes the messages that have been sent. So a message has an ID and a destination. We don't store the source. We could store it, but it's not really necessary to verify this protocol. OK. Then we have this gen state command, and the reason that's there is not really needed, but I want to show what's going on behind the scenes is that Veil kind of creates lean definitions. So effectively, it's driving lean to create some structures that you can then reason about. So what this does is it creates this ring state structure that is the type of your state. I also have this set visualizer thing. I'll show what that is for later. OK, so we've defined the type of the state, basically the variables declaration in TLA. And now we define the initial state. Now, one big difference between Veil and TLA is that Veil has this imperative modeling language. So you see here we are describing the initial state as an imperative action, basically. When you start, you do this. There's a syntactic convention that capital letters mean universal quantification. So this says, for all n, set the leader relation to false. For all m and n, send pending to false. So basically, no messages, no leaders in the beginning. Next, we specify the transitions. So transitions are also specified imperatively. We have support for two-state transitions like TLA, but the support is not as extensive as imperative transitions. I can describe that later. So you have transitions. This protocol has 2 transitions, send and receive, effectively. And there's this ghost relation here. You can think of it as a definition to help us manage complexity, right? So this says next is the next node in the ring from n. Don't have to go into the details. So the protocol works as I described. When it starts, every node sends its own ID to the next node in the ring. And then the rules of the protocol are when you receive a message with ID, which is called sender here, so this is a guard here. Require is a guard, right? And OK, there must be this message in the message soup. And when we do that, well, OK, we remove that message from the message loop. This is not really necessary. We could delete this. And then we do the logic of the protocol. If the ID is our own ID, we become the leader. Otherwise, if it's greater than our own ID, then we forward the message to the next node. Is that reasonably clear? Okay. And then the safety property we want to specify and verify is the following. As I mentioned, capital letters are implicitly universally quantified. So what this says is for all n and m, if n is the leader and m is the leader, then they're the same. So basically, there's at most one leader, right? Now, the usual thing to do when you write a model is you want to, before you try to verify that, prove that the model actually satisfies this property, you want to model check it. So Veil has this model check command. And what model check does is it runs an explicit state model checker similar to TLC. And you have all the kind of fancy visualizations of how the search progressed, similar kind of table to TLA, action coverage, everything you'd kind of expect. So let me introduce a bug, this trivial bug in the protocol. And what we get here is a kind of counterexample trace that this property can be violated. Now, let me fix the protocol and show you something else. Symbolic model checking, similar to Appalachi, the way this is exposed in Veil is through this SAT or trace language. So what we're saying here is we are defining this or declaring the shape of a trace, saying, oh, there's a way of doing any tree actions in this protocol such that at the end there's a leader. And what this does behind, and we're saying this is a trace this protocol should admit, it's a satisfiable trace. And what this does behind the scene is it encodes this as an SMT query and sends it to an SMT solver, and it gives you a satisfying trace, right? We can also do kind of bounded symbolic model checking and say, oh, there's no way of doing any 5 actions such that there are 2 leaders, right? And again, if we kind of break this again, we should get a counter example here, right? Now, final thing I want to show, yes?
But this is not for the 7 nodes.
Yes, so this is a symbolic kind of example. Yes, good point. So what's happening here is we're not checking the specific instantiation with 7 nodes. This is unbounded in the number of nodes, but bounded in the depth of the trace. Thank you. Now, okay, let me fix the protocol again. Final thing I want to show, is, let me delete this, check invariance. Okay, this is automated kind of proofs of the safety property. So what it does is it tries to check whether the safety property is inductive. And in this case, it isn't. So what you get is a concrete kind of counterexample to induction. You see the pre-state, or this is a pre-state that satisfies all the invariants. In this case, there's a safety property. You do this transition, you get into a post-state that doesn't. So let me tell you now, show you what the visualizer thing was for. That it defines a TypeScript. It's a TypeScript kind of React component that lets you plug into this widget here and shows you some like custom visualization for your protocol. I'm not going to go, in the interest of time, in the details of how this helps you come up with an inductive invariant, but the idea is you can remove these counterexamples to induction one by one. So I'm going to remove one. And you go to the check again, and you get some other counterexample to induction. And basically, by removing, you have to think a bit to understand how to remove these. But by removing all of them, you eventually come up with an inductive invariant. Okay. Veil is a verifier for distributed protocols embedded in Lean, has a TLC-style explicit state model checking, symbolic model checking via SMT, interactive proofs in Lean using Lean tactics, and a small trusted computing base. Now, I promised at the beginning of the talk to talk about performance. So what's the performance of the verified model checker like? So we compared it, we translated, I think, like 12 or 16 specifications from TLA to Veil, and we compare it. So we have a model checker is called LACE. It's a formally verified parallel model checker. For Veil, it's both sound and complete, and we've proven it in Lean, so it's complete, assuming no hash collisions. And it uses a map-reduce parallelization strategy because it's easier to verify than fine-grained concurrency. And we claim it has highly competitive performance. So let me show you some plots. So LACE is in red, TLC is in blue. The top part of the plots shows absolute running time. Lower is better. So for most specifications, we're kind of better than TLC. So the bottom part shows relative speed. So bars going down is LACE being better. Bars going up is TLC being better. Let me zoom in on a few of these plots to make the point a bit clearer. So these are specifications of Paxos variants, multi-Paxos, Paxos, and network ordered Paxos. We're generally faster than TLC, about 2 to 3 times faster, but we're not always faster than TLC. So some specifications, we're not exactly sure what's going on here, but we suspect it's because of the map-reduce parallelization strategy. The reduce step here is taking a lot of time. So you see LACE basically sometimes, like for simple allocator, becomes worse the more threads you add. But overall performance is quite competitive, and we think this is a good model checker. Although I have to mention it only checks safety. For now, we don't have liveness support in Veil yet. Okay, takeaways. Veil is a multi-modal verifier for distributed protocols. It combines explicit and symbolic model checking with automated and interactive proofs in a single cohesive tool. It has a high performance verified concurrent model checker, and we're hoping to add liveness support and refinement reasoning later this year, hopefully. Thank you.